All right, here's problem-solving advice that I would strongly suggest kind of sticking to. Some people have tried not to do it. It generally does not work out well for them. You're going to first identify all the objects in the system that apply to the conservation of momentum. So what are the objects involved? What's colliding? What's not? Generally, for what we're doing, we are going to be ignoring friction or any energy lost to heat or sound. So for the most part, our momentum is actually going to be conserved, but kind of keep it in the back of your head, like it does not necessarily need to be conserved, but the problems that we're looking at it is. So this next part's especially helpful. You're going to draw a sketch of the before and after interaction, and for each picture, you're going to write a momentum equation. So we're looking at what are all the objects, what is the momentum. So if the object is by itself, it gets its own equation. If there was a collision and it's stuck together, then the objects together get an equation. They don't get one separate if they're stuck together. Now it's one object, one mass. You're going to assign positive and negative directions in your picture. This particularly refers to velocity. All right, velocity has its speed with direction, and that matters because your momentum depends on the direction you are moving in. If two objects are moving toward each other, one of them is going to have a negative velocity. So next, I'm not looking for you to memorize equations like, oh, this is an explosion, so this is the equation, right? So on the page before, we had a list of these equations, right? This one versus this one versus this one. I'm not looking for you to memorize that. I'm looking for you to understand how you would set that up. And I feel like it's so much easier to use the pictures versus trying to memorize which equations go with which type of collision. You're going to determine the momentum of the objects before and the momentum after. You're going to set the before and after equal, and then you're going to solve for any unknowns. In some problems, you may need to use energy and momentum. When these problems come up in your homework, definitely put a star next to it because for sure on the final exam you will have one like that, and it's very likely on the AP exam as well that comes up, as it has done so for many tests. Okay, so we have a 2,000 kilogram car traveling at 20 meters per second. So we can go ahead and draw the car. Super fancy. And it's moving this way at 20 meters per second. We have another car, not as massive, and it is at rest. So we have a second car, and its speed is 0 meters per second. Right? This is the before picture. Okay? So this is what's happening. I have a car at rest. I have a car in motion. Then, right, there is a collision, and it wants us to find the velocity of the smaller car after the collision. So this collision occurs, and the big car still has speed. It is now going 6.67 meters per second, and then the little car now has speed, but I don't know what it is. How many pictures do we have? We have 4. Okay, this is the before, and the before equals the after, and we're going to write a momentum equation for each vehicle. So this car was 2,000 kilograms times 20 meters per second plus 1,000 kilograms times 0 meters per second equals 2,000 kilograms times 6.67 meters per second plus 1,000 kilograms times velocity. All right. So next, we go ahead and do the algebra. We're looking to try to figure out what this velocity is. So then on the left-hand side, when we multiply, we end up with 4,000. And by 4,000, I mean 40,000 kilograms times meters per second equals 13,340 kilograms times meters per second plus 1,000 V. We subtract, we divide by 1,000, and the final velocity is going to end up being 26.7 meters per second for that car. So let's talk about the relationship here before we move on. We have this big car. He's only going 20 meters per second. He hits the little guy and he slows down. So he has lost momentum. So by himself, his momentum is not conserved. He had 40,000. That's what he started with. And then he lost momentum. He now only has 13,340 kilograms times meters per second. So he lost momentum. In order for momentum to be conserved, that means the small guy gained momentum. Now he's not as massive, so his velocity really shoots off. Okay? So the momentum, when we talk about conservation of momentum, it is a before collision, after collision. The objects by itself, they do not conserve the momentum. So the big car's momentum was not conserved. It was the system of the car that is conserved. So it is a system, not an object. Objects' momentums are not conserved in collisions. That's a key point. All right, next one. We have a snow-covered road. The car has a mass, and it collides head-on with a van. Do you guys know what head-on means? Head-on collision? Right? They're facing each other, and they collide. That's a head-on collision. So what we have here is a car. And I'm going to say he's moving this way. And does it say how fast he was going? Nope. All right, so this is my V. I don't know that. The velocity of the car. And then I have a van. And I do know the speed of the van. The speed is 8 meters per second. But this is where we need to be careful. What is the direction the van is going? Good, toward the car. And therefore, I can see here, I'm like, oh, you know what? I have to pick one of these to be positive, one to be negative. I'm going to make this one negative. So we have negative 8 meters per second. So we're writing the velocity here, not just the speed. All right, so here's the next piece then. After the collision, they lock together and immediately come to rest. So we will be neglecting friction here. So if they lock together, now they're kind of combined. Okay, so they're combined as one object. So how many momentum equations am I going to have to write? 3, because you're going to write one for each picture. Now let's see, what else do we have? They immediately come to rest. So here, this is 0 meters per second. So we go through. So I have mass. This is going to be 1,100 kilograms because this is in scientific notation. So we're just moving the decimal 3 times. And then that's times V of the car plus the mass of the van is 2,500 kilograms times negative 8 meters per second. Now generally, I have my equals here. Generally, I would just say 0, right? Because it's mass times velocity. But for the notes in this particular example, I do want to talk about if we were really writing the equation here, because we have one object, they don't tell us like, oh, together this is how much they weigh. We need to determine that by simple addition. So this is just going to be 1,100 kilograms plus 2,500 kilograms. But in this situation, this is going to be 0 meters per second because it comes to rest. So then we get 11,000 times the velocity of the car minus 20,000 kilograms times meters per second equals 0. We add to the other side, we divide, and that initial velocity of the car is going to be 18.2 meters per second. All right, next example. We have a rifle, and it's going to be firing a shell. Now, before that rifle fires the shell, where is the bullet located? inside the rifle. Oopsie, sorry. So the bullet is inside the rifle. And this is the before situation. In this one, this is an explosion, right? So we have these two together, then it explodes, it becomes two different objects. Now we have the rifle by itself, and then the bullet is in motion. So it's a 4 kilogram rifle with a 20-gram shell, so that's going to be 4 kilograms plus 0.02 kilograms. What is the velocity before it shoots? 0. So this is 0 meters per second. And then that's going to equal, we have 4 kilograms. Okay, now if you shot anything, what happens to the gun? Yep, there's a recoil, and that is what we're looking for. We're looking for the recoil velocity of the gun. And that direction is in the opposite direction that the bullet is moving. So the bullet goes to the right, recoil goes in the opposite direction. So that's VR plus the mass was 0.02 kilograms of the bullet, and now it's moving at positive 300 meters per second. So we get 0 equals 4 VR plus 6 kilograms times meters per second. And when we solve, we get the recoil velocity is negative 1.5 meters per second.